Hello everyone and welcome back to this next lecture. So the past several lectures we talked about several concepts, right? We talked about how we can synthesize transfer functions. We talked about two different types of transfer functions. That is the transfer function between the current and the output current and the reference current, and the transfer function between the output current and the disturbance grid voltage. And we have talked about the impact of these two transfer functions and what that means to the performance of the controller. Also, we have talked about the concept of stability. That is, what happens when we increase the control gain beyond a certain limit, the system becomes unstable. How do we detect that? Can we predict it using some method? We saw both two techniques, using the poles of the closed loop system, that is the roots of the characteristic equation, as well as through a Bode plot in the form of phase margin and gain margin. Now in this lecture, let us try to sum up all these things we learned to be able to design, or try to design rather, the best possible proportional controller. So let's go back to this control that we have, right? That is the frequency response.py. Now the best part is in this one file we have everything, right? We have all transfer functions. We have our plant model, we have the different transfer functions, we have the sampling delay, we have taken almost everything into account. Or at least we have taken so many things into account as is necessary to design or at least analyze a decent amount of detail in this system. Right? There are still several other factors which we may not have taken into account. For example, the inductor will have several other things such as core losses and hysteresis losses, which we do not consider, right? Those are fairly complex to add as well. So let's come over here and see what we need to do. So the first question we need to ask is, to be able to design the best possible controller, what do we expect from this control? So let's go over to our command line and see what all we've got. So let's take a look at this. We have printed out all the different transfer functions. We have printed out the current expected due to the reference signal. We have also printed out the current expected due to the grid voltage. Alright. And we have finally a stability analysis. Of course, the poles of the closed loop system can be found either from this as this method, that is as we can find out as the roots of the characteristic equation, or we can find out the stability of the system through the gain and phase margin, which are in the form of Bode plots. So we will use all these. Now the question is, how do we do that? So first and foremost, what do we expect? For this controller to be as good as it gets, we want the current due to the reference signal to be as close to the reference as possible. Now, for example, what that means is, let's go over to our file, and we have chosen a reference of 10 amperes. Well, actually I don't have it here, but if you look at the converter control, we are looking at a reference magnitude of 10 amperes. And if you look at 10 amperes multiplied by square root 2, that comes to around 14 point something, because square root 2 is 1.414. So we have a peak of 14.14. So with respect to this peak of 14.14, the question is, we want a magnitude, that is the magnitude here is the peak magnitude of the output current, to be as close as possible to 14.14, and we want the phase angle to be as close to 0 as possible, because this phase angle is the phase angle delay of the transfer function. If the phase angle delay of the transfer, or rather this is the phase angle due to the transfer function, right? So this takes into account the phase angle of the reference as well as the phase angle of the transfer function to produce the phase angle of the output current. So we want this phase angle to be as close to 0 as possible, because we've considered a reference of 0 phase angle. Now this would mean if this is close to 14.14 and the phase angle is 0, this means that our output current due to the reference is as close to the reference as possible. Now the next part is, we also know that the grid voltage impacts the output current as a disturbance. Now to be able to assess that, we need to know again what will be the magnitude of the current due to the grid voltage and what will be the phase angle of the current due to the grid voltage. Now in this case, however, most important is the magnitude, because the grid voltage is a disturbance and we want to reject this disturbance. So it doesn't matter what the grid voltage is, we want the current to be as small as possible, right? As small as possible. The smaller the better. Because if it is as small as possible, that means the only current, or rather the only component that affects the output current is the reference signal, which is what we want ideally, right? Now, after all this, the next thing we want is, this is the performance of the controller. This is the steady state performance of the controller. But the controller has to be stable to begin with. And that's where stability analysis comes in. So we want to make sure that the roots of the closed loop, or rather the poles of the closed loop system, are in the left half of the S-plane and sufficiently in the left half of the S-plane, and the phase and gain margin through the Bode plots are sufficiently large. So already, as we talked about, we want the gain margin to be in the range of 5 or above, and we want the phase margin to be around 40 degrees or above, right? So with these, let's get started. Let's take some few values. So for example, right now we have a value of 12. We know it's unstable, so let's not do that. Let's take a value of 2. So we do know that this works, right? So we are at least starting with something that works. So let me clear the screen and run it again. Alright, so we can look at it through two ways. We can look at it from the command line as well as from the Bode plot. So let's start with the command line. So as I already said, we don't really need these transfer function anymore. So we can start here from the currents. So the current due to the reference signal. We see that the magnitude is 13.43. And as I said, the reference has a peak of 14.14. So even though it's close, we would like it a little closer, right? Because 13.43 is almost a 1 ampere difference, which is like almost a 10% error, right? That's pretty high. You want the error to be less than 5%. Now, the phase angle is around minus 9 degrees, also a bit on the large side, but this could be acceptable, right? Now, the next thing is, what about the current due to the disturbance, the grid voltage? The magnitude is 10 amperes and the phase angle is minus 90 degrees. Now, the phase angle, as I said, doesn't really matter that much. What matters is the magnitude. 10 amperes is just too high, is simply too high. That means that the magnitude of the current produced by the grid voltage as a disturbance is almost as high as produced by the reference, which means the disturbance is as strong as your reference signal. That's not a good sign, right? You don't want your disturbance to be as powerful as your main reference signal. So this is obviously not going to work. Alright. Now here, however, the good sign is we have enough stability margin. Look at our stability margin. Our poles are well into the left half of the S-plane. We are looking at minus 4000. So now that we are done with this, let's look at our Bode plots. Now we can look at the first one, that is a forward transfer function. So the forward transfer function, we've already looked at this. At 50 Hertz, we have a fairly large control gain. So we can even zoom in here and have a look. Actually, I can just maximize this. And we've already seen this part. It has a fairly large control gain at 50 Hertz. So we saw it's already in the range of around, it's in the range of 6. Actually, 6 is not very large. So that's the first red flag that you see here. At the operating frequency, the magnitude of the forward transfer function, that is the transfer function which is the product of the controller and the plant, is only 6. That's not very large. You want it much larger than 1. Alright. So going back here, you see, however, that we have a fairly large gain margin, which is 5.05, and we have a phase margin which is 70 degrees. These are fairly good numbers. Right? The reason why we have 5.05 is because our gain at minus 180 degrees is in the range of 0.2. So remember, the gain margin is the reciprocal of the actual gain at minus 180 degrees. So these values are okay. We have a fairly stable system. So this is okay. I'll close it down. Now let's look at our closed loop system. This is the closed loop system, and these values are very similar to what we have read off from our command line. So from our command line, we already know these, right? This is where we calculate it from. So these two, what this actually means is that, number one, the tracking of the output with respect to the reference is, though decent, can be better. Alright? Because remember, like I said, we still have a 1 ampere error just with respect to the reference. Right? This is a fairly large error. We would like this current to be close to around 14. So this is a pretty large error. Now in terms of the grid voltage, we see that at the operating frequency, the impact of the grid voltage is fairly large. So look at the curve here. This is the magnitude of the grid voltage impacting the output current. So this is the transfer function of the output current with respect to the grid voltage, and this is the magnitude. So the magnitude is continuously increasing until it reaches some kind of a peak here, right? The peak happens at around 1 kilohertz, 1000 hertz. So which means at 50 hertz, this magnitude is fairly large. Alright, now I'll talk about the significance of this a little later in the next few lectures when we conclude on this particular control strategy. But for now, what is important is because it is rising and at 50 hertz, it has risen sufficiently large enough that this disturbance grid voltage is strong enough to impact your output current. That is how you interpret these frequency response plots, right? And you can see that impact from the console, that we have this huge current, right? Now we've already seen the simulation results, so there is no point looking at it again. Let's move on to another value. This is a good starting point since we've already seen this. So now the question is, if this is not good enough, what do? Let's increase this. Let's make it 4, right? Now let's make it 4, clear the screen, run it again. And we have a new set of results. So let's look at the command line now. So the command line says that now our magnitude is 13.82, which is better than before. So now our error is around 0.4, around 0.4. 0.4 is still okay. 0.4 is reasonably okay because it's well below 1. So now our error probably is less than 5%. And that's a good sign, right? The phase angle is -4 degrees, which is also much better than before. Before we had a phase angle delay of -9 degrees, right? So now the output lags behind the reference by just -5 degrees. So this is a pretty good tracking. But remember, this is only the impact of the reference on the output. We need to look at this as well. Now the current due to the grid voltage disturbance has this magnitude, right? 5.20. Now remember, this is way better than before. Before we had a value of 10, right? A value of 10 is pretty bad because that means it's almost as strong as your reference. Now we have a value which is just around 1/3 that of the reference. The problem is it's still pretty big, right? This magnitude of 5 is still quite big. So you still have a fairly strong impact of the grid voltage, but it has decreased. Alright, so now that this is done, let's look at the stability analysis. The good part is the poles are on the left half of the S-plane and significantly in the left half of the S-plane. So this is good news, right? Now let's look at our Bode plots. So always start with the very first one. These are our Bode plots. Now, one thing you can see, our gain margin is now quite bad. Alright, this is quite bad. This is 2.53. So what this means is that at the 180 degree phase angle shift, we have just a gain of 0.4, right? Now, here again, this is where you as a control engineer have to use your judgment. It's like driving a car. You have to judge how much distance you want to leave from the car in front of you, right? Simple as that. For example, as you're driving, sometimes you see a truck in front of you, you want to leave a lot of space, right? Because trucks are not something you want to go close to. So as a driver, you decide how much space you want to give with respect to the car in front of you, how safe it is. And as a control engineer, you also have to come up with similar amount of judgment. Now, in my opinion, this is very much on the border. A gain margin of 2.53 is very much on the border. You need at least 3. Alright, we need at least 3 to be safe. But I would suggest, for now, pause the video and try to simulate this and check for yourself what you get. Alright, so go ahead and pause the video and try it out, and I will tell you another control strategy. So I assume you have checked out the result for yourself. Now let us instead check out what happens if we choose an intermediate result. So for example, let's say for example we make it 3. and we run it again. So we have another set of results. Let's look at again the console. So the magnitude is 3.7. Again, we have an error of around 0.5, which is decent, which is still less than 1. So we have an error which is maybe around 5%, right? So we are on the borderline as far as error is concerned. Phase angle delay is -6 degrees, quite decent. So our reference is fairly, or rather output is fairly close to the reference. Now what happens to the grid voltage as a disturbance? The magnitude is 6.88, right? A little worse in the previous case, but still better than the first case where the magnitude was 10 amperes, right? But now this is again probably unacceptable, right? Because this is enough to completely disrupt our simulation, or rather our performance. So now, of course, let's go ahead and check out what else we get. The stability margin is now much better. As you can see, they're well into the left half of the S-plane and even further left from the previous case. Let's check out our Bode plot and let's see what we get here. Now, the good news is our gain margin has improved. We have a gain margin of 3.37, right? This is better than what we got before. What we got before was very much close to instability. I wouldn't want to go that close. This is a little better. Phase margin also close to 60 degrees, much better. Right? If I was a control engineer, I would choose this as a safe control design, right? So now what I'm going to do, I'm going to close these plots and go out and do it in the simulation. And let's verify for ourselves if this is better. So let me go and change this. Go to the web browser, click on the run button. So I'll go to the terminal, check it out, no errors, we are good to go. So all we have to do now is go and plot on the current comparison. So let's go to the file browser and we have this. So this is what we get. Let's have a look. The orange line is the reference current. The blue line is the output voltage. As we have seen from before, it's now closer, but like I said, because of that 6 amperes, because of this 6 amperes produced by the grid voltage and at quadrature, this has completely disrupted the tracking performance of the controller. Alright, so it is probably better than what we got before, but still this is not acceptable, right? And in terms of performance of a controller, this is simply unacceptable. So the question you would ask is, what do we do? In such cases, what we need to do, we need to surrender. We need to say that this proportional controller that we were trying to design is just not good enough. We need a slightly better controller. And that's what I'm going to start in the next lecture. I'm going to start trying to design a PI controller for this same entire system. Using everything is exactly the same, only replacing my controller with a PI controller, which is a proportional integral controller. So in addition to having a proportional gain, I also have an integral component multiplied by an integral gain. So let's check out how that works. So I hope this entire process is a little clear to you. Of course, in any control design, there is always an element of judgment. It is impossible to remove judgment completely from control, because control is very much a design process, and any design requires some amount of judgment, some amount of you thinking for yourself what is okay and what is not okay, right? So as time goes on, this judgment gets better, and that's all you can hope for. So keep trying out different controllers, keep honing on your own skills, and you'll find your judgment getting better bit by bit. So if you have any doubts about what I did, please do post in the Q&A forum and I'll be happy to help you out. Otherwise, I will see you in the next lecture where we will get started with a PI controller. Thank you so much and see you soon. Goodbye for now.